Good afternoon. We're going to resume with um, quadratic functions, and again, we'll be alternating between the standard form of a quadratic function as well as the vertex form. And again, just looking at the basic features of what we have with quadratic features as well as added features, we have from section 2.1 on page 249. And among the exercises we have, in the case of number 10, okay, we got the function k of x. Now we got the vertex form of this particular quadratic function presented. And again, for the vertex form, we have like y is equal to f of x, or in this particular problem, we have y represented by k of x. And we have in the form of a times the square of the binomial x minus h, followed by the addition of k. And looking at what we have given for k of x specifically. So we have 2 times the square of x minus 3, followed by the subtraction of 2. And just looking at what we have among the features. Okay, so we have for the leading coefficient a, okay, that is equal to 2. And the sign value of the leading coefficient is going to dictate the direction upon which the graph of the quadratic function will open. Okay, so we have that a is equal to 2, and 2 is a positive number, and we have in the leadoff, okay, we have the direction to which the graph of k of x is going to open, and since the leading coefficient is positive, okay, we're going to have that k of x is going to open upward. And for what we have in the case of the values of h and k, now we have x minus h is represented by the binomial x minus 3. And for the value of h, that is going to be the value of x whenever x minus 3 is set equal to 0. Okay. So if x minus 3 is 0, we have the x is equal to 3. And again, the x and the h exist as 1, where we have the x is equal to h is equal to 3. Okay, and for the solution in setting the binomial x minus 3 to 0, okay, we have, again, x is equal to 3, and this is going to be the axis of symmetry. And again, the axis of symmetry is going to be the vertical line that divides the graph of what we have for k of x into equal sections. So we have for the axis of symmetry, okay, we're going to have the x is equal to 3. And in the case of what we have for the value of k, alright, so I have that k is equal to negative 2, and again, we have h equal to 3, and k equal to 2. So for what we have in the case of the vertex, okay, so we have hk is going to be at 3, negative 2. Okay. All right, and again, I had interchanged the order of the terms, so the axis of symmetry is actually part F, and the vertex was part B. And in the case of what we have with the other portions, and we have concerning part C officially as well as part D, okay, we're dealing with the determination of intercepts. And for what we have in the case of part C, okay, we're looking for the x-intercepts. And again, for each x-intercept, we're looking at setting the y value to 0 while solving for x. And now we have, for this function, okay, y is represented by k of x. So I will set this equal to 0. And we have is equal to 2 times the square of x minus 3, followed by the subtraction of 2. And again, I'm solving for x, but right now we have x situated as part of the binomial x minus 3, which we have to be squared. Okay, so looking at what we have here, so we have a quadratic equation, and if I isolate the variable expression, so I can undo the subtraction of 2 upon adding 2 to both sides. So I have it 2 is equal to 2 times the square of x minus 3, and if I divide the whole equation by 2 just to get the right hand solely in terms of the square of x minus 3, okay, so this will come down to 1 is equal to the square of x minus 3. And what I'm going to do here is reverse the order, kind of go from b is equal to a is equal to b format. Okay, so I have the square of x minus 3 is equal to 1. And if I follow through with the square root property of equality, like have x squared is equal to p, and transitioning to x is equal to plus or minus the square root of p, well, we'll have the square of x minus 3 to go to x minus 3. And as for 1, we'll be taking the positive and negative square root values. So for x minus 3, at the upper end it will go to positive 1, and at the lower end it will go to minus 1. And looking at what we have for the values in x, okay, so we have at the lower ends we have the x minus 3 is equal to negative 1, and at the upper end, okay, we have that x minus 3 is equal to 1. And if we have x minus 3 equal to negative 1, and also x minus 3 equal to 1, I can treat both equations isolating x upon adding 3 to both ends. So we have for x minus 3 is equal to negative 1, okay, we're going to have x equal to negative 1 plus 3, which will be at 2. And if x minus 3 is equal to 1, well, x is going to be 1 plus 3, which will be at 4. Okay, thus there will be 2 x-intercepts. And they can be expressed in terms of x equals or explicitly in terms of ordered pairs. So we have for the x-intercepts, so we have x equal to 2 as well as x is equal to 4. And again, at specified points, okay, again, for each x-intercept, okay, we have the y value to be 0. So you have 2, 0, as well as 4, 0. And for what we have in the case of the y-intercepts, again, the general ordered pair expression, okay, is going to be 0y. And we are referencing, okay, the exact same function, and this time setting x to 0. So here we're going to have that y is equal to k of 0 and that is equal to 2 times, okay, the square of 0 minus 3. And followed by the subtraction of 2. Right, so I have 0 minus 3 is going to be negative 3. And in following through, okay, so we got 2 times. Now the square of a negative is going to be a positive. So square of negative 3, you have negative 3 times itself, so this will be a positive 9. and we have 2 times 9 is 18. Take away 2, and we have the y value to end up at 16. All right, so we have here, okay, we got 2 x-intercepts and 1 y-intercept. Okay, so you have the y-intercept. You can say either y is equal to 16 or have it as the ordered pair 0, 16. All right, so we have at least 4 key points. Okay, we have the vertex, which we have at 3, -2. And again, we have a couple of x-intercepts with 2, 0, 4, 0. And of course the y-intercept, which we have at 0, 16. And just looking at this from a visual perspective, and again, now just for the intro, okay, so the graph is going to open upward, and it is divided into equal sections, okay, by the axis of symmetry, which we have at x equal to 3. And again, the axis of symmetry always passes through the vertex. Okay, now for the nature of the graph itself. Okay. So looking at what is present, okay, so you got k of x is equal to 2 times the square of x minus 3 followed by the subtraction of 2. Okay, so for the graph, okay, I have opening from the vertex, which we have at 3, -2, and we have the other points. Okay, we have the intercepts on the x-axis at 2, 0 and 4, 0, and we have a y-intercept at 0, 16. And again, the graph is divided into equal sections with respect to the axis of symmetry. Again, we have this at x is equal to 3. Okay, and if I were to supply any additional point or points, okay, we can use the axis of symmetry as a guideline without having to do any calculating. Okay, and so if you notice, we have from the vertex, you have 3, -2, and once we go up, let's say to the x-axis, you notice that we have 2, 0 is one space to the left, 4, 0 is going to be one space to the right. And if I were to find out, okay, what a fifth point is going to be, and you could take, let's say, the y-intercept, and if you notice, okay, we have just getting level at y is equal to 16. So on the axis of symmetry, again, we have at 3, 16, and we have as a point to the left with the y-intercept is 0, 16. So this is going to be 3 places to the left. And if I were to mirror across the axis of symmetry and say going 3 places to the right, so right across from 0, 16 and equidistant from the axis of symmetry, we can say that on the right half of this parabola and level with the y-intercept, okay, we're going to have this order pair to end up at 6, 16. Okay, so the y-intercept, 6, 16, the intercepts, and the vertex will make up 5 points on the graph. This particular function, which we have with k of x, is equal to 2 times the square of x minus 3, followed by the subtraction of 2. Now, for what we have in the case of the next function, and we have for number 12, okay, so we're going with still a different letter, okay, and again we have with the layouts in the vertex form. So we're going from f of x to k of x to where we have with r of x, and we have, okay, so you have r x, okay, we have just lining up, say proportionally. Okay, so we have for r of x in number 12, okay, we have given as 1/2 the square of x plus 2. So just looking for the same features, okay, as in case number 10. Okay, so you have a is going to be at 1/2. And just like 2, it is a positive number, a smaller number, but one that is still positive. And just like k of x from earlier, the graph of r of x is also going to open up. And for what we have in the case of determining what the values of h and k are, okay, so k is going to be void, okay, and we'll get to this in just a moment. But here we have x minus h represented by the binomial x plus 2, and if I set this equal to 0, okay, so you have x plus 2 is equal to 0, and your axis of symmetry is going to be x equal to -2, and we'll get to that. And again, your h value is the resulting x value. Okay, so h and x, again, one and the same, and we'll have the value -2. And so we have for the axis of symmetry, we have the x is equal to -2. Okay, and if you notice, you have 1/2 lines up with a, x plus 2 is lined up with x minus h. But if you notice, we have a void. Okay, nothing follows the square of that which represents x minus h. And since there's nothing added or subtracted, okay, we're going to have that the value of k is 0. Okay, so we got h at -2 and k at 0. So we're going to have for the resulting vertex, okay, this is going to be an x-intercept. Okay, so this will come out to -2, 0. So -2, 0. Okay, that is on the x-axis. And looking at what we have in the case of the intercepts, and okay, if we got the setup right, which we do, okay, we've already got the x-intercept, but I'm just going to kind of repeat the process here. For the x-intercept, again, we have the general coordinates at x, 0. Now, when we work with k of x in number 10, okay, we had 2 x-intercepts, okay, and very likely it's going to turn out we're going to have just one x-intercept in this type of function. Okay, so we have r of x to represent y, and for the x-intercept, okay, this will be where y is at 0. And so you have 0 is equal to 1/2 of the square of x plus 2. And if I multiply the equation by 2 just to get rid of the fraction, so working with what we have here, so we got 2 times 0 is 0. We got 2 times 1/2 is 1. And then we have times the square of x plus 2. Okay, so we got the variable expression by itself on the right, 0 on the left. And what I'll do here is just switch the order. So we have the square of x plus 2 on the left and 0 on the right. And again, utilizing the square root property of equality. So if I go from the square of x plus 2 to just x plus 2, we have equal to plus or minus the square root of 0. And 0 is neither positive nor negative. Okay, now there is such a thing in math, okay, where you're dealing with like very small positive and negative values, where you have like infinitesimals, positive infinitesimals, negative infinitesimals, have like plus 0.0000 and like negative 0.00, but we're not dealing with this stuff because the square root of 0 and only 0 is going to be 0 itself. So you have x plus 2 is equal to 0, and from this we're going to have only one x value. So we have x equal to negative 2 . So you have for the x-intercept, we have x is equal to negative 2, and as an ordered pair, we have negative 2, 0, and it's going to turn out that this is exactly what we had established with the vertex. And so the vertex turns out to be the one and only x-intercept. For what we have in the case of the y-intercept, okay, so for the y-intercept, okay, we're looking at what y is whenever x is at 0. So here, y equals r of x is going to be y is equal to r of 0. And we have is equal to 1/2 of the square of 0 plus 2. Again, x is at 0. And so we've got 0 plus 2 is 2. And 2 squared is 4. And we'll have half of 4 is equal to 2. So we have for the y-intercept, we have y is equal to 2, or if you're to express as an ordered pair, okay, we're going to have 0, 2. Okay. So just for this particular layout, okay, we're going to have only 2 distinct points identified. Okay, and we can supply some additional points. And looking at what we have in the graph of this quadratic function. Okay, so you have only 2 points identified, the vertex and the x-intercept. Okay, you had to be the same with just negative 2, 0. And before we had more points already identified since the vertex was distinct from the x-intercepts, and we had 2 x-intercepts and a distinct point with the vertex. So we had 3 points already laid out, and the y-intercept, another distinct point. Okay, that supplied a 4th point. Whereas here, after all this work, we have only 2 distinct points readily identified as belonging to the graph of this quadratic function. And if I look a little bit further into this, and again, just like number 10, again, we have the graph to open upward, and the axis of symmetry we have at negative 2, 0. And this is going to pass through the vertex location. Okay, so the axis of symmetry we have at x is equal to negative 2. Again, the graph opens upward, and this graph again represents 1/2 of the square of x plus 2. Now, just to kind of fill in, okay, now we had 2 points readily identified. Okay, that was the vertex and the x-intercept, which are 1 at negative 2, 0. And we had the y-intercept at 0, 2. And now, if I were to supply any additional point, okay, so if I go up to y is equal to 2, okay, so you have just kind of like level with the y-intercept, so you have like a point at negative 2, 2. Okay, so this point is level on the axis of symmetry with respect to the y-intercept. If you notice, from -2, 2 to 0, 2. So I'm going 2 spaces to the right. And if I mirror across and go 2 places to the left, I have this other order pair, which is at -4, 2. And if I were to go up, okay, and in this particular case, now I had selected, let's say, a value of x, say at 4, and I chose like this particular value. And if I choose x at 4, okay, so again, your y values is going to be 1/2 of 4 plus 2, with 4 plus 2 raised to the second. And if I think of x set to 4, now you've got 4 plus 2 is 6. And 6 squared is going to be 36. And half of 36 is going to be 18. So when x is 4, your y value is going to be 18. And so we have this particular order pair. So think of it like this. Okay, so if I go up to y is equal to 18, so -2, 18. Okay, so if I go from x equal to -2 to x is equal to 4, I'm going to the right 6 places. And guess what? With 418 already determined, if I mirror across and go back 6 spaces, so I'm going from x equal to -2 to x is equal to -8. So -818, 418. Okay, those points mirror each other across the axis of symmetry. So these could be 5 points among infinite points that will make up the graph of what we have in the case of R of x. All right, now in looking at what we have alternating between standard and vertex forms of quadratic function presentations, and we've got again for quadratic functions, again we have f of x, or y is equal to f of x is equal to ax squared plus bx plus c, whereupon a does not equal to 0. Okay, so again, this is going to be the standard form. And once again, we have for the vertex form, again, you still have the same a, and you have times the square of x minus h, followed by the addition of k, and just like what we have in the standard form, for there to be a square expression, okay, the leading coefficient a, strictly speaking, cannot be 0 either. Okay, so again, this is going to be the vertex form. Now, for what we have in the case of number 17, okay, now, sort of different from what we had in the example. Okay, we're going to have a coefficient other than 1 in front of the x squared term in the standard form. And we got the function, okay, to be p of x. We have p of x, okay, another way of saying f of x or y. And p of x, okay, we have is equal to 3x squared minus 12x minus 7. Again, this is going to be the standard form. And looking at translating to what we have in terms of the vertex form. So what I'm going to do first of all is to put parentheses around the variable terms. So p of x is equal to the quantity of 3x squared minus 12x, followed by the subtraction of 7. Now, we had this stage which was regarded as where we are looking at applying the completion of the square. And this is possible if you had the leading term in the parentheses to be just x squared or whatever we have as the letter to the second power without any coefficient in front of it besides 1, if there has to be a coefficient placed. But for what we have here, we don't have x squared in the lead off, but we got 3x squared. So I'm going to go ahead and factor out 3 from the parentheses. So we just have in this modified write-up, we got p of x, and again for 3x squared minus 12x, okay, so we have 3. 3 will go into 3x squared, x squared times. 3 into negative 12x will go minus 4x times. And once you have the first term in the parentheses, okay, to be x squared, we're now at the stage whereupon we can apply the completion of the square. Okay, and for the completion of the square, okay, again we have first term in the parentheses, we have an x squared. Now for completing the square, we look at the coefficient that is next to the first order x. So we got CTS, shorthand for completing the square. So for the completion of the square, you take the number that is next to x and divide by 2 and square out. So you got negative 4 over 2, that's going to be negative 2. And the square of negative 2 will be 4. And so it's taking what we have now, okay, so we have with the number 4, okay, that is going to be added to x squared minus 4x. Okay, and I will mention, okay, so I'm adding 4 in the parentheses. Now in the big picture, I'm not adding 4. Thanks to the coefficient 3 that is on the outside. So as I'm adding 4, I'm actually adding 3 times 4. So 3 times 4 is 12. So as I'm actually adding 4 within, I'm adding 12 overall. So to offset the surplus that is created, so if I'm adding 12 at the front, I'm going to have to take away 12 at the back. In other words, subtract 12 from negative 7. All right. And you can do a little bit of a double check. Okay, so for right now, we got 3 times x squared minus 4x plus 4 and negative 7 minus 12. Okay, so this will be negative 19. Okay. I'll just show you. You can do a little bit of a double check. Okay, so again, you want what we have here to be on the same page with what we had for the standard form. So just kind of doing a quick check. You got like your p of x. Okay, so you got 3 over x squared minus 4x plus 4. So you got 3x squared minus 12x. 3 times 4 is 12 minus 19. We got 3x squared minus 12x, and 12 minus 19 we have at minus 7. Okay, so we're on the right pathway. And so we're going to transition from the standard form to the vertex form. And in the case of p of x, okay, we're going to have the square trinomial with x squared minus 4x plus 4 and with x squared minus 4x plus 4. Okay, so and again, we're going to have the vertex form, and looking at the characters that will be inside the parentheses. Okay, so again with x squared, again we have the square of x, and what would form x squared minus 4x plus 4? Okay, we'll have along with x. Okay, now again we had added 4 to x squared minus 4x, and how did I do that? Well, this is upon the completion of the square step. Okay, and we had taken the square of negative 2 to get to 4, and whatever I square from the completion of the square stage, okay, this is going to reappear. So we have 3 times the square of x minus 2 followed by the subtraction of 19. Okay, so this is going to be the vertex form of what we have from the introduced standard form of this quadratic. All right. Now, for what we have in the case of number 20, okay, so now have in standard form, we've got the function d of x. So we have is equal to negative 3x squared okay, so you have negative 3x squared equal to negative 3x squared minus 9x plus 8. And just taking what we have now, okay, so we got for d of x. Okay, so if I separate the variable terms apart from the constant, okay, and again, so I'm going to be going from the standard to the vertex. Okay, and if you notice, okay, just like I had factored out 3, we're now in a situation where we have the first variable term is with the coefficient negative 3, which is instilled within the parentheses. Okay, so I'm going to factor out the negative 3. And so we're going to have in the rewrite, okay, so we have d of x and we have negative 3 times the quantity, so we have x squared, and negative 3 into negative 9x is going to be a positive 3x. So we have followed by the addition of 8. And looking at what we have with the completion of the square. So after factoring out negative 3, the first term in the parentheses we have as x squared. Okay, so looking at initiating the process of completing the square. Okay, so we have 3, and whatever's next to x, I'm going to divide by 2 and square. So we got the square of 3 halves, and the square of 3 halves is going to be 9/4. and for 9/4. Okay, so that's going to be added to 3x. Okay, so we have for d of x, we have -3. We have times the quantity of x squared plus 3x plus 9/4. Yeah, plus 8. Now, I'm going to look at, again, just creating another operation of balancing what we have at the front and the back of what we have on the right hand side of the equation. So as I'm adding 9/4 inside the parentheses, again, in the overall picture, I'm not adding 9/4, I'm actually adding -3 times 9/4, which essentially is applying subtraction. So -3 times 9/4, so this will be -27/4. So guess what? I'm creating a bit of a deficit at the front, and to override the deficit, what I'm taking away at the front, I'm going to add at the end. So in this case, I'm going to have 8 plus 27/4. So just looking at combining 8 and 27/4. Okay, so we got at the moment, okay, so we got d of x. We have -3 times the quantity of x squared plus 3x plus 9/4. Again, just over to the side here, we have for 8 plus 27/4. Think of like 8 over 1 plus 27/4. And 8 over 1 in terms of fourths is going to be 32/4. And 32/4 and 27/4 will make 59/4. Okay. So 8 and 27/4 will add up to 59/4. And again, if you have any trepidations about this particular stage, again, you can double check. Okay, so you have the case of d of x. I want this statement to balance out to the standard form we started with. Okay, so distributing, so you got -3x squared. We got minus 9x. And we got -27/4. We have plus 59/4. So we got -3x squared minus 9x. -27 plus 59 is going to be 32 over 4. And so we're back to where we started from. -3x squared minus 9x plus 8. So this is kind of like, in a way, for the lack of a better term, it's a bit of a reverse engineering approach to make sure that we're on the right track. And so for d of x, okay, just one more step, and we're going to come out to the vertex form. So we got -3, and x squared plus 3x plus 9/4 is going to be a squared trinomial. Okay, and okay, so we got the a value at -3. The k value is a non-integer with 59/4. And for this trinomial, okay, this is going to be the square. Okay, for x squared, we have the square of x. And for the rest, okay, again, just referencing what we had in terms of even able to get to this trinomial, I had added 9/4, which came into existence upon squaring out 3/2. So that which I square out, this is going to reappear in the vertex form. So I'm going to have -3 times the quantity. I'm going to have x plus 3/2 quantity squared plus 59/4 and again, so this is going to be the resulting vertex form. All right, and we'll be looking into like zeros and multiplicities of polynomials. But I tell you what, just for the next few moments, I tell you what, let's see what we get. As you look at converting to vertex form. Now say we have for the first function, okay, we'll say we have f of x is equal to x squared plus 6x plus 29. And we'll say that we have for the second function, we'll say that we have g of x is equal to, we'll say we have -4x squared plus 16x plus 31. Both of these are in standard form, so let's see what we get for the vertex forms of what we have for f of x and g of x. Okay, just for just some items to mention. Okay, now both f of x and g of x are presented in standard form, and for the pathway to getting to the vertex form, okay, we have with f of x, okay, we have the first term is x squared, okay, and once you separate the variable terms apart from the constant, which we have at 29, we're able to go directly into the completion of the square right away, whereas in the case of g of x, okay, if you were to group the variable terms, notice you have like the -4 in front of the x squared, and because we have a coefficient other than 1 that's in front of the x squared, it does kind of create a situation where there's going to be additional needles to thread before we get into the completion of the square. So you got that bit of an added layer of complication thanks to the -4 in front of the x squared as opposed to the clean x squared from f of x. And if we go ahead and say just look into what we have for f of x is equal to x squared plus 6x plus 29. So if we separate the variable terms apart from the constant, okay, so you have f of x. Okay, so you have the quantity of x squared plus 6x, and we have followed by 29. Okay, and so first term in the parentheses, okay, we have x squared, so there's nothing to factor out. So I can go ahead and jump into the completion of the square. Okay, so again, whatever is next to the first order x, I'm going to take half that number and square. So you got 6/2 is going to be +3. And +3 squared comes out to 9. So here we're going to have f of x is equal to x squared plus 6x. Again, 9 is going to be added. yeah, plus 29, but again, I need to create balance. Okay, because if I don't do anything, to add or subtract away from 29, we'll have x squared plus 6x plus 38. But I want to get it back level to what we have with the standard form. So to override the surplus at the front, I'm going to take 9 away at the end. So here I'm going to have f of x is equal to x squared plus 6x plus 9. And we'll have 29 minus 9 is going to be at 20. Okay, so I need this plus 9 so that I have a squared trinomial, which I'm going to need to determine what binomial will be squared. Okay, and you can always double check. So you got x squared plus 6x plus 9. And you got plus 20 is going to make 29. So I'm back at the same level as what I have with the standard form. And looking at what we have upon moving forward. So x squared plus 6x plus 9. Again, it's going to be a squared trinomial. Okay, so like your a value is 1 and the k value is 20, and for that which is going to provide the formation of that which refers to x minus h. Now again, from x squared, I'm going to have the square of x, and in the case of what I have, that will make the formation of this square trinomial possible. Again, after separating the variable terms, I had added 9, and the 9 was created upon the completion of the square, where I had the number, namely positive 3, to be squared. Again, this is going to reappear and be inserted in terms of addition. So we have f of x is equal to the square of x plus 3 followed by the addition of 20. Okay, so that is going to be, once again, the vertex form. Okay, now for what we have in the case of g of x, okay, so I have negative 4x squared plus 16x plus 31. And if I separate the variable terms, so that g of x okay, so I have negative 4x squared plus 16x. I have the plus 31. And then if I factor out negative 4, okay, so I have g of x, so I have negative 4, and factoring out negative 4 from negative 4x squared plus 16x, I'm going to have x squared minus 4x. I have plus 31. Okay, and so I can set things up in terms of completing the square. So I got negative 4. I have times the quantity of x squared minus 4x. Okay, so for the completion of the square, so the first term in the parentheses is x squared. So taking the coefficient next to the first order x, I have the number at negative 4. And again, for the completion of the square, okay, so I have half of negative 4, square out. Half of negative 4 is going to be negative 2, and negative 2 squared is going to be 4. And that number, negative 2, that is going to resurface. Okay, so for right now, we got g of x. I have negative 4 times the quantity. So I have x squared minus 4x and within the parentheses. So I'm going to add 4. And plus 31. And again, just making some adjustments. Okay. Because of the coefficient -4 on the outside, whatever add to the parentheses, it's not going to be what's done solely at the front. Instead, we have -4 times 4. So I'm actually placing -16 at the front. So I'm going to balance this by adding 16 at the end. So now I have g of x is equal to -4 times the quantity, where we have x squared minus 4x plus 4. And we got 31 plus 16 is going to make 47. Okay. And so just sort of doing a quick check. So I got -4x squared is minus 4x squared. -4 over -4x is plus 16x. -4 times 4 is a -16. -16 plus 47 is 31. Okay. And going past this checkpoint, okay, we're ready to establish the vertex form. So you got your a value at -4. The k value is going to be at 47. And for that, which will represent the square of x minus h, now we got with x squared, then we have the square of x. And again, in terms of how this trinomial came about, with the completion of the square, we had the 4 to originate from squaring out -2. And I said that -2 would reappear, and so it does. So for the vertex form of this function, we have g of x is equal to -4 times the quantity of x minus 2 squared, followed by the addition of 47. Okay. And so that will be that vertex form once again. All right. Now, looking at what we have now, okay, just a little bit of continuing and moving on with factoring, and also tied in with a bit of expanding. Okay, we're going to have for the next portion, and we'll be looking at zeros and multiplicities. Okay, and just in this capacity, okay, so I have forming polynomials from zeros and multiplicities. Okay, now for that term, multiplicities. Okay, we have the singular version of this. Okay, have multiplicity. Of a zero. And in the case of what we have with the multiplicity of a zero, okay, so this is going to be regarded as the degree. To which the factor corresponding to that zero is raised when f of x, or whatever our function is expressed in factored form. Okay, and just to kind of provide a bit of an intro to this. Okay, say if I were to be determining a factored and expanded form of f of x and say we have given the following. I'll say first of all, okay, we'll say we have just a couple of zeros. We'll say we have -1 and 5, and we'll say that we have for the degree of the function okay, we're just going to have this at 2. Okay, and looking at what we have in terms of establishing factored and expanded forms. Okay, so think of like -1 and 5. You think of this like working backwards. See, we have x is equal to -1. We can say this will come from setting x plus 1, or any direct multiple of x plus 1, equal to 0. And for the number 5, that this is regarded as a 0. Think of it like the zero product property worked in reverse. You got the solution, and how did I get to the solution? Well, this be like setting x minus 5 equal to 0. And so for a factored form of f of x, and so we have f of x, and this is going to be a second degree expression that has these zeros. So factors, we can say will be x plus 1 and x minus 5. Okay, so if I were to set, say, this function equal to 0, well, if x plus 1 is 0, we got x at -1. If x minus 5 is 0, well, we got x back at 5. So we have one factored form of f of x with these zeros. Now, for the expanded form, this would be like if you took away the parentheses and FOILed out the multiplication between x plus 1 and x minus 5. So if I were to FOIL out, I would have like x squared minus 5x plus x. Last part is at -5. And combining the like terms in the middle. Okay, so we have an expanded form. It's going to be where we have f of x is equal to x squared minus 4x minus 5. All right. Now, where multiplicity might be mentioned or specified, say have where there are zeros. Okay, say we have just 0 with a multiplicity equal to 3. Now say we have negative 2 with a multiplicity equal to 2. Now say we have as another 0. Okay, we'll say we have 2 with a multiplicity equal to 1. And we have for the degree of f of x, we'll say that the degree is equal to 6. Okay, so just taking what we have here. So we got with our zeros. So we got 0, -2, and +2. So think of it like working in reverse. If we have x equal to 0, but we got the x factor. For -2, we can say this stems from x plus 2. And if we got 2, we can say this stems from setting x minus 2 equal to 0. Now, we got with the multiplicities. Okay, so we got 0 with a multiplicity of 3. So you can regard this as x to the third. -2 with a multiplicity of 2. From -2 I have x plus 2. But with a multiplicity of 2, I'm going to have not just x plus 2, but in effect I'm going to have x plus 2 raised to the second. And we have it x minus 2 multiplicity of 1. This is just going to be plain x minus 2, or x minus 2 to the first. So we have as a factored form and emphasizing the multiplicities. So we have f of x is equal to x to the third. Again, the third degree emphasizing that the value of 0 has a multiplicity of 3. And we have times the quantity of x plus 2, which will be raised to the second. Again, we got the 0 at -2. Second degree refers to the multiplicity of -2. And finally, we have x minus 2, which is to the first, and you just leave that as x minus 2. So this is a factored form of a polynomial that has those zeros and multiplicities. And to get to the 6th degree explicitly, I'm just going to expand on out. Okay, so we have x cubed, and we've got the square of x plus 2. So I'm just going to write this in terms of multiplication. That times x minus 2. And there's no one right way to go about this. What I'm going to do is I'm just going to cluster together the first two and the last two factors. Okay, so you have f of x. Now for x cubed times the quantity of x plus 2, so I'm going to have x to the fourth plus 2x cubed. And for x plus 2 times x minus 2, we're going to have x squared minus 2x plus 2x. Those will cancel, so I have minus 4 and looking at foiling out, so we got x to the 4th times x squared, so this will be x to the 6th minus 4x to the 4th, and we have plus 2x cubed times x squared, so this will be 2x to the 5th, and the last product, okay, so you have minus 8 x cubed. And so we have, for the expanded form, now you can have what you had immediately above, but we can just have the terms all arranged in descending degree order. Okay, so we got x to the 6th, so you have corresponding to the 6th degree, and you have plus 2x to the 5th, next highest order term. And then we have minus 4x to the 4th, and last we have minus 8x cubed. Okay, so this will be an expanded form of a polynomial that has these characteristics.